We have talked about first order reactions, and in first order reactions, the main focus was on radioactive decay. But what if you have a zero order reaction? And before addressing zero order reactions, let me write one. So one would be the decomposition of gaseous ammonia into nitrogen and hydrogen gases. Now, this decomposition takes place on on a surface. It's a part of surface chemistry. Uh, and for now, just assume that there you put a catalyst, and catalyst increases the rate of a reaction, and this happens at an incredibly high temperature, and ammonia decomposes into its constituent gases. Now, in this reaction right here, increasing the concentration of ammonia, of the reactant, does not increase the rate. So that means that this reaction is actually zero order. Zero order. So that means that you can write rate to be equal to K times NH3, the concentration of NH3 to the power 0. Now, given this fact, you can always just cancel everything out here since it's just one. You can write the rate to be equal to the rate is equal to K. Now, in theory, you cannot just only apply this to just decomposition of NH3, but any reaction in general. So let's take a general reaction, A going to products. A reacting somehow and going to products, and let's this be a zero order reaction. Now, due to this, the rate is equal to K times A to the power 0, and this is something that we don't need to write. This is just one. And the rate itself, the rate right here, is the rate of usage of the concentration of A. So minus dA over dt. So now you have a differential equation, and the differential equation is written like this. Negative of d concentration of A over dt equals K. Take this negative sign here to the other side, and take this dt from here. Let's make this dt to disappear and take it to the other side. Now you have two differentials. Related by a linear expression, and the way you would solve this differential equation is by taking limits with integration. So you're integrating both sides. Now, initially, the time on the right hand side, the time starts as being 0, and it goes to being, let's say, capital T. And initially, the concentration of A is A naught, and let's say at time t it goes to some random concentration A at t. Now, if you evaluate these integrals, they would come out to be AT minus A naught equals negative of K times T minus 0. And further simplifying this, you can write this further as A at T is equal to the concentration of A initially minus KT. And this represents the concentration time dependence for a zero order reaction. And let me just write the word zero here just to avoid any confusion. So zero order reaction. Now, similar to what we have done in finding out the half-life of a first order reaction, we were talking about radioactive decay in that, you can also do the half-life for a zero order reaction. So in this case, the half-life would be when A at T half, that's how we represent half-life, that's equal to half the reactant, half the concentration of the initial concentration of the reactant. And if you plug this into this expression in the Bing expression that we have got, you have A naught over 2 equals A naught minus KT. And this is, by the way, this is T half. You are replacing T by T half as well. And if you do the math, if you simplify this further, so you have kt half equals a naught minus a naught over 2, and that's also equal to a naught over 2. Now what you can do finally is, given you have the rate constant, you can find time, the half-life, to be equal to a naught over 2k. You took this k and took it to the other side. And this is the half-life for a zero order reaction. And so that means if you go on and plot this zero order reaction concentration time dependence, you actually have something like this. So let the y-axis represent the concentration and the x-axis represent the time. So time, concentration. Now initially the reaction starts off with some initial concentration, and since the reactant is getting used up, there is lesser reactant after some certain amount of time. You actually see a downward line. And why do you see a line? Well, since you can always write, let's just take the expression that we had here. So you have A at t equals a naught minus kt, and let's replace the t here with capital T as well, just to make everything uniform. So what you have is here, this is your y variable. This is what you represent on the y-axis. This is what you represent on the x-axis. And if you look at this carefully, and the equation of the straight line is equal to y equals mx plus c. So y here corresponds to A, x here corresponds to capital T, c here corresponds to capital A naught, and m here corresponds to negative of k. That's a bit messy. So let's draw that in a different color. So m corresponds to the negative k, that's right here. Then you have the c to be corresponding to this a naught that you have here, and you have this x corresponding to the x, and you have the y corresponding to the y. Great. So that means you have an equation, and c is the y-intercept. C is the y-intercept here. Just a beginner's introduction to straight lines. So this is the y-intercept. Y-intercept is a naught, and this graph decreases with a slope. In this case, would be negative of k. Now you can go on and do some problems. Let's take a very generic made-up problem. So if you started out with a naught to equal to 1 molars, and a goes to some products, and you need to figure out in how much time is all of a used up, given the rate constant is let's say 1 into 10 to the power negative 3 second inverse, and you need to figure out, oh sorry, this here would be moles per liter second, since that's the unit for the zero order reaction. We looked at it in a previous video. Now you need to figure out if this is the rate constant and this is the initial concentration, how much time does this reaction take to complete? So again, what you can do is you can take a t equals a naught minus kt, and a of t here in this case is 0. We are looking at complete reaction, so a of t is 0. A naught is equal to 1 moles per liter. 1 molar is just that. And k here is equal to what we have. So you can write this as 0 equals 1 molar minus, instead of k you put in 1 times 10 to the power minus 3 molars per second times t. And you solve this, so in the end you would get t equals 1 molar over 1 into 10 to the power negative 3 molars per second, and that is equal to 1,000 seconds, and that's roughly equal to about 20 minutes or so. That's roughly equal to somewhere about one third of an hour. And the main takeaway from this video should be that you can write the expression of the time dependence of the concentration of the reactant in a certain reaction. And what you can also do is you can find the half-life. That's really easy. However, one thing that you need to keep in mind is that not many reactions in real life are zero order, as it might seem from the simplicity for these reactions. There are, in fact, really humongous amounts of reactions that do not occur with the zero order. See you in the next video.